Okay, so hello everyone. I'm Maura Pintor, and I'm a postdoc at University of Cagliari. And welcome to a new event for our series on machine learning security. Today's guest is Sven Gowal, and I just want to share a few things before we start. First, the event is live streamed and recorded. So if you don't want to be recorded, feel free to follow from YouTube. Then for question policy, we encourage questions. First, we prioritize questions on the call, so Zoom call. Raised hands are preferred options, then the chat. And of course, we also look at the comments on YouTube if there's time to answer. For knowing about the new events we organize, feel free to check out our links. There is a Twitter account, a LinkedIn account, Eventbrite, and also a website that posts the new events. And I'll paste the links in the chat as soon as we start. If you feel like you want to know more about machine learning security, we also have a course recorded, and you can find it on the same YouTube channel where we are live streaming right now. And lastly, I want to thank all the people who helped me organize these events. And now I leave the stage to Antonio, who will introduce our speaker for today.
Okay, thank you, Maura. Thank you a lot. Good afternoon to everyone. My name is Antonio, and today we are really pleased to have with us Sven Gowal. Sven got his PhD at EPFL in 2013, and now he's a staff researcher engineer at DeepMind in UK. He's actually working on robust and certifiable machine learning. He has co-authored over 30 papers in the domain of robust machine learning, and notably, he also received a 2 Best Paper Award in very prestigious conferences. But now I suppose that the audience is waiting to be delighted by your presentation, Sven. So therefore, Sven, I would leave the floor to you. Thanks.
Thank you, Antonio and Maura. Well, thank you everyone for joining this event. And I will just share my screen. Thank you for the introduction. So can you see everything all right?
Yes, yes.
All right, thank you. All right, so the subject of my talk today is around trying to make neural networks robust to adversarial and natural distribution shifts using specification-driven machine learning. You will see it's a fancy word for things that you probably already know. And I will try to give a bit more context about what we've been doing at DeepMind in the past, 3 to 4 years, with an update on our latest work. Obviously, if you have any question that you don't want to share through the Zoom meeting, feel free to contact me by email. I'll also be at NeurIPS this year, so if you want to meet in person at that point, feel free to also drop me a message. So I think the audience here is probably very familiar with what I'm going to say on this slide, but we all know that machine learning models are not really robust. And despite achieving superhuman accuracy on benchmarks like ImageNet, models are susceptible, one, to small adversarial perturbations that are invisible to us, but they're also very prone to learning shortcuts and basically exploit spurious correlations that are present in the training set to increase their performance on that particular data set. So when a new distribution comes about during inference, and if that distribution differs from the training distribution, you're about to see some errors that the model has, and those errors we would like to basically remove them or avoid them as much as possible. And so on the left here, you can see the classical example of adversarial examples, where a panda is basically being classified with 99% confidence as a gibbon with a very small amount of perturbations on its pixels. And on the right-hand side, you can see more intricate examples of, camels that are usually appear in the desert and that are misclassified as another animal when there is snow. Or if you search even on Google for, weddings, you will end up with lots of Western weddings and maybe miss some important features of, other weddings in other countries. And finally, for the left-handed people, if you search for a mug, again, you'll get most handles on the right and very few mugs with handles on the left. And so if you don't train your model to be robust to these, rotations or translations or flips of the image, you would expect basically a classifier to be unable to classify a mug if the handle appears on the right, on the left. Sorry. And I wanted to also highlight that these issues are not specifically limited to ImageNet models. So even models that have been trained on large amount, web scale level amount of data also have some issues. In particular here, I showed the example with Clip, where adding a piece of text basically in the image will actually force Clip to output a different classification. We also have the examples of models in production that can be fooled. Here's a simple example where elongating the horizontal bar of a 3 will make the system of a Tesla think that it's an 85 miles an hour speed limit instead of 35. And also I wanted to highlight that this is not particular to vision models, and these things arise as well for text classification. And this is a rather, an early example of this, but you can see that models make very weird and egregious mistakes and are highly biased into the way they complete sentences. So what is the problem? The problem is that we train model with data or experience in the case of a reinforcement learning agent, and that data or experience is a bit by definition limited, so finite, and also potentially biased. So no matter how you collect, if you're this data tends to be biased in this talk, but there's also the case where you just train, if you just do vanilla training and you obtain your agent or model at the end of training, you kind of expect the model to end up to be biased and non-robust and unsafe, and also recently, basically private information. And really the solution that we've been applying all along is to specify some rules, to give some specification when we train our models. So for one, with data augmentation, which is kind of a form of specification, such that when we train our model, despite the fact that the model is biased and limited, we still are able to obtain models that are unbiased, robust, safe, private, calibrated, and so on. And so in the realm of the specification-driven machine learning, if you will, you really have two main components. One is around basically formalizing specification. So here it's about providing a language that will describe what behavior we expect from the model. And typical, specifications that people have used is, adversarial example should not alter the predictions of a classifier. Synonyms, like replacing synonyms in a sentence, should not change the meaning of that sentence. Uncertainty should always increase as sensor noise increases. Or you can go a bit more semantic level and say, lighting condition or skin tone shouldn't affect classifier performance. And once you have formalized the specification and you have maybe a mathematical definition of what those look like, you would want to enforce the specification. And here it's all about deploying and developing methods and for training machine learning models that would be compliant with these rules and specifications. And of course, the core, the simplest one to think about is data augmentation. Again, in this example of the mug with the left and right handle. For adversarial example, you can think of adversarial training, and you can also go down the route of doing model certification and verification. So in this talk, I will start by just going through what we've done more recently at DeepMind in the context of adversarial training. I will skip a bit the part on model certification, but I welcome questions if you have any on that topic. And I will finish by basically expanding the realm of these LP norm bounded perturbations and going into more semantic perturbations, how to evaluate model more broadly and in a more open-ended manner. So
Sven?
Yeah.
Sven, sorry for interrupting you.
Yes.
May I suggest you to turn off the camera so that in order to have a more stable connection?
Oh, I see.
Oh, sorry for interrupting you in this.
Yeah, no worries. Well,
okay.
Feel free to interrupt me if if I drop out.
Okay. Thank you. Sorry again.
Yeah. Is there any particular slide where it was not intelligible and I should go back, or?
No. Actually, yeah, it was fine, but from time to time it may happen. So we would like to avoid it for the future slide. Actually, that's why I asked you.
Sounds good. Sounds good. So in this particular part of the talk, we're really interested in a very well-formed definition of for a specification. And we're going to use the context of adversarial examples and more particularly LP norm bounded perturbations to study how we could train models to become robust and to satisfy specifications. And so we're interested in imperceptible perturbation, that is perturbations that will have an LP norm that is smaller than some threshold, where the threshold is usually fairly small. Typically, the P that you use in the LP norm is infinity or 2. There's also L1 and L0, which have been widely studied in the past. So formally, we're interested in minimizing the adversarial risk. That is, we want to find a classifier such that we expect as possible on examples that are worst case examples within some bound. And so what that means is that effectively for each example of my training set, I'm going to try and find a direction for the gradients of the parameters such that my specification stays true. And I could say the output should remain a 9 for all images that look like this image of a 9 plus some noise, plus some bounded noise. So mathematically speaking, you can basically write this as this expression for S here on the side. And the way people have trained, I've been training this, basically is this, trying to lower this loss, if you want, is, and basically maximizing solving this inner maximization problem is by running a procedure called projected gradient descent, where you start with an initial basically random guess for the perturbation, and then you create a better guess through iterations by following the gradient and reprojecting to the LP norm ball around your example. And finally, once you have an adversarial example for each element of your batch, you can now optimize the outer loop by basically now minimizing, let's say, the cross entropy in the case of the classification task on these adversarial examples. So I'll first start by going through a brief overview of some of the challenges of adversarial training, and then we'll detail one solution to basically address some of these challenges. So one of the earliest, I'd say, challenge that has been well documented is the trade-off between clean and robust accuracy. Tsipras and others demonstrated through a toy scenario that, in fact, robustness could be at odds with accuracy. And really, what this demonstrates is that models, like by training models to be robust to adversarial example, it kind of eats a bit of the bandwidth and the capacity of these models, which have to focus on very specific adversarial example, which may not arise in reality. And as a result, they kind of have to trade off with clean accuracy deployment. However, in practice, it also has been shown that using small epsilons for these NP norms can be in fact beneficial for generalization. And this is work exemplified by Sihang, Xi, and others. And here's a plot kind of demonstrating a bit how the trend between clean accuracy and robust accuracy has evolved over time. Each of these dots is a model that has been submitted to the Robust Bench leaderboard, where we basically plot on the x-axis clean accuracy, so accuracy on unperturbed examples of the test set, and then on the y-axis, the robust accuracy, which is the accuracy against an adversarial perturbation for each example of the test set. And you can see that, as time went on, models became better and better. And in fact, like the trade-off appears very much at the end here in the case of CIFAR-10, where really for the last few percent, you need to finally drop either robust accuracy or clean accuracy and trade off between the two. But in general, with larger model and more data, we've been able to go beyond this trade-off in some sense. And this links up nicely to the next challenge, which is about capacity. And so this was already empirically observed, but also theoretically, it has been explained in the case of the fact that there's an inherent relationship between the size of the neural net in some sense and the smoothness that neural net can achieve. And here again is a plot exemplifying this sort of trade-off between capacity, where on the x-axis you have the number of parameters of a model, here a wide ResNet and a ResNet. And on the y-axis, you have the test accuracy, and you can see that as the number of parameters increases, we can increase the robust accuracy. And that is the case without extra data or with extra data that we've gathered from an external data set that resembles CIFAR-10. What you can also observe is that capacity will get you some way, but not all the way. So the curve very much flattens down as you start adding more and more parameter. And in fact, we've tried even training much bigger models, but the performance wasn't as good as what we would have hoped. And so finally, the last challenge is really about using more data and the fact that robust training requires more data. This was also demonstrated by Schmidt and others that robust training will require polynomially more data than standard training. And here again, we have an example of a plot where here we test and train on exactly the same distribution. This is a distribution that comes from a generative model, which I will detail a bit later in the talk. But you can see where so the fact that we have a generative model allows us to add as many examples as we want during training. And the fact that, even with 2 million sample, we cannot overcome the 70% robust accuracy on CIFAR-10-like images is a bit disconcerting. And just to give a point of reference, 50K is basically the usual data set size for CIFAR-10. And here, by increasing by a factor 40, we can just about get an extra 10% in terms of robust accuracy. So this leads me to the first contribution that I like to share, which is around improving robustness using generated data. This is joint work with a number of people at DeepMind. So again, you can feel free to either reach out to me or reach out to them in case you have questions. So motivation for this talk was really is really shown in this plot here. For this paper is really demonstrated in this plot. So around the end of about 2 years ago, we had released a paper where we had tuned very well like a number of different models on CIFAR-10, and we've observed that the difference between a model that has been well trained, well tuned on CIFAR-10 without extra data and with extra data was actually quite big, here around 9%. And so we wanted to see whether we could leverage the training set to a greater extent and basically close that gap of 9%. And so we basically have three core contributions. One was to demonstrate that it was actually possible to use generated data, even of very low quality, to improve robust accuracy. The second one was around leveraging higher quality generated input, so better quality generative model, and see what happens. And finally, we demonstrate that this can significantly improve the state of the art on CIFAR10, and that the method also generalized to CIFAR100 SVHN and ImageNet. The core strategy is fairly simple. The idea is to take your training data set, in our case, the 50,000 images of CIFAR10, train a known robust classifier, and train a known unconditional generative model. These two steps can be, of course, collapsed into one by training conditional generative model. But for the purpose here, we'll assume those are two separate steps. And finally, from the unconditional generative model, we can generate a number of inputs. And from the non-robust classifier, you can generate a number of labels for those inputs. That gives you a generated data set that then, merged with the original training set, gives you a new training set that on top of which you can train your robust classifier. And so the first idea that we had was just to not even try to use very complicated, generated, like very high quality generated input. We started with just fitting a standard Gaussian, multivariate Gaussian on the different classes of CIFAR10. And you can see some samples here on the slide, where here in the second row, you have images of cars. So you can tell that that image with cyan color here kind of looks like a car, but it's really far from, a high quality input of what you would consider a car. And we saw that even by adding 20% of these generally quite low quality generated inputs with 80% of the original data set at every batch, we were in fact able to improve robust accuracy by roughly 1%. And just to give a bit of perspective, 1% is about the difference between training with standard adversarial training and training with trades, let's say. So from the point of view of like how big that gap is, it's quite significant in terms of that particular benchmark. The plot on the left here shows basically what happens to the robust accuracy as we vary the proportion of real data versus generated data at each batch. So all on the right, you basically only use real data, and all the way on the left, you only use generated data. And you can see that obviously there's some front and there's an optimal way of merging these two data sets. What we develop in the paper is a number of sufficient conditions that kind of demonstrate why this might work. The conditions are like, the first one is obviously you need to have some accurate pseudo labeling mechanism. So that is the classifier, the non-robust classifier that you train on the original training set should do well on the test set of CIFAR10, which is usually the case. So you can easily train models that are above 96% accurate. And then you have one or two cases. Either you're extremely limited in terms of capacity of your robust model, in which case, obviously, you would want that the generated data and the real data are distributions are as close as possible. But what saves us is kind of, as you increase the capacity of the model, this condition kind of splits in two, where all you need to have now is basically the fact that adversarial examples are unlikely, in the sense that if I sample from the generative model and my pseudo labeling system is correct about that sample shouldn't be an adversarial example. And we've seen over and over again that it's very difficult to generate adversarial examples just through random sampling. So we assume this to be relatively rare. And finally, the last condition is about the fact that you want to have a non-zero chance of sampling a real image from your generated model. And this just explains that obviously, even if you have a very poor generative model, as long as you're able to generate from time to time images that look reasonable, you're going to get information from these samples, especially if they're correctly classified. And so the next step was basically to take a number of state-of-the-art generative model, again, run this sweep on the different proportions of samples between generated and real samples at each batch. And you can observe here, so the four models that we've considered are the basically variational autoencoders, GANs, both big GAN and style GAN, as well as the more recent diffusion probabilistic models. And you can see that the diffusion model here in green actually is the best and offers basically the images of highest quality, and shows that you can in fact increase for that particular model, which is the wide ResNet 2810, you can increase the robust accuracy by more than 6% by adding generated data. And one of the most interesting point in this plot is probably on the far left, where you can see that even by using only generated data, you can actually do better than if you use only real data. And that's the case because you're able to generate a lot more generated samples than you have training data available. And in this particular plot, we sampled 1 billion samples for each of these points here. Finally, I wanted to show basically this table where we tried the exact same technique on CIFAR10 with different norms, so either Infinity or L2, as well as CIFAR100 as VHN, Tiny ImageNet, and ImageNet. We can see that in all cases, we're able to improve the performance of models and improve the robust accuracy quite dramatically. One observation, though, is as the data set becomes more complicated, so as you go down towards ImageNet here, the performance gain becomes smaller. And obviously, that goes to show that, the likelihood of actually generating a correct real sample basically becomes smaller as the data set becomes more complicated. So that ends up this first part of the talk around training models that are robust and that will satisfy some well-defined specification. Now I'm going to go into the topic of trying to formalize specification that are not necessarily LP norm based. And here we really want to go beyond these LP norm perturbations, which are limited in terms of pixel changes, to more semantic level perturbations. And here's a case of an image that is classified at 99% as not smiling, where by adding, basically changing the lighting condition to some extent, we can make the classifier think that that person who was not smiling originally now is smiling with 100% confidence. And this goes beyond basically these LP norm, and we would like to be robust to translations, rotations. It could be brush stroke width on these digits, lighting condition as I've shown above, or even different skin tones for different faces. And the second contribution I wanted to talk about was this one, which was already submitted a while ago at CVPR, but is around achieving robustness. In the paper, we contributed basically a formalization in some sense of what exactly we mean by variations of interest and arbitrary variations. We demonstrate that we can indeed create models that are robust to these variations of interest by using and leveraging the tools that we already had at disposal for LP norm bounded perturbations, where we can again leverage our usual toolbox, which may be adversarial training or verification. And we provide evidence that you can indeed train models to be less biased to the perturbation of interest. And the original motivation for this work was really the gender shade study that demonstrated that face classifiers that were available online were highly biased, either towards gender or biased towards skin tone. And so really the only thing that we're trying to do here is to change the definition of the adversarial risk, which I've shown in the earlier slides, by instead of considering only transformation in these LP norm balls, we're going to consider transformations that are part of this set T. And this transformation can be arbitrary and operate on the input X. And this set of transformation obviously should be transformation that should not alter the label Y. One way of formalizing this, again, there are many ways of formalizing this exact subject, but one way we went about is just to say we have some generative model that can basically take some input in latent space and create an input in terms of the image space. And that latent space is decomposed into two spaces. One basically one part of the coordinates basically encodes or affect the labels, while the other part doesn't. And so more formally, what that would mean is that the distribution of Y given X is basically only dependent on these Z parallel, which would be the set of latents that are relevant to the label, and totally independent from the set of latents that are basically irrelevant. And so now you can basically write now the set of transformation that you care about, which is basically from given an image X that it can be decomposed into these two sets of latents, you would want to be robust, or your classifier shouldn't change its classification if you change the set of the coordinates that correspond to the irrelevant list. You can, of course, define adversarial risk in the same way that we have done before, just here replacing the X with the output of the generative model. You can also do it more in the expectation sense, where you randomly sample basically relevant latents and sample new examples as you go along. So one will be called admix and the other one randmix, just in case. So far, I haven't explained how we get basically this space of the irrelevant latents. And the rest of this section is going to be about basically defining this. And one way of implementing adversarial mixing in the context of this work that was inspired by gender shades was to use StyleGAN. So at the time, StyleGAN basically was the best model to generate faces. And it kind of inherently provides a disentangled representation that allows to control coarser and finer details using style mixing. So you can see some example here on the right, and where you can basically mix coarser features from a given face with like finer structures of another face to get a new composite, if you want. And of course, there are works that operationalize admix in different ways. There's of course work from Wong and others that used conditional variational encoders. There's also work around perceptual adversarial training or adversarial augments, which basically can be recasted in the same way. And all these formalization are basically equivalent. So the way we implemented, again, using StyleGAN was to take, so let's say you have an original image that is in your training set that you're trying now to modify to basically input throughout your training procedure. You're going to take that original input, you're going to mix it with a set of random latents that you've randomly sampled. So basically those will compose a set of irrelevant latents, and you're going to take the relevant latents from your original clean image. This allows you to synthesize a new face or new image. You can now classify that new image, and you keep iterating over this procedure until you find basically a set of irrelevant latents that would get misclassified, that will constitute your new adversarial example that you can then use for training. And so there's a bunch of additional results in the paper on more toy examples, but the final experiment was to demonstrate its usefulness on the Celebet dataset, where we look at a number of attributes, where attribute number 2 here is the smiling attribute, and where we compare nominal training, which is just using images from the training set, with adversarial training with L infinity perturbations of different size. and rand mix and adversarial mixing. And you can see that across these 4 attributes, in any case, adversarial mixing seems to have the best performance. One study that we haven't included in the paper, which is worth noting, is that when we actually specifically split the CelebA dataset into darker and lighter skin tones, we've observed that the gap between the accuracy obtained on the lighter skin types and the darker skin types reduces significantly when we use adversarial mixing. So that brings me to the last part of this talk, and and then I will take on the questions. So so far we've basically gone about trying to build adversarial examples from an anchor. In the case of the panda, that was that original image, clean image of the panda. In case of that person that wasn't smiling, it was that original person. And then building an adversarial perturbation that we can add to that image to generate and synthesize a new adversarial example. And you can think of the perturbation, or the Pinot perturbation, or more semantic perturbation, as explanations potentially of why a classifier might suddenly switch its decision. And obviously, these visual explanations sometimes can be useful, but they're very much left to the interpretation of the user, and makes it relatively hard to interpret and to basically act upon. And so we really wanted to see if we could go beyond one anchoring the failures to an original data set, and to going beyond visual that users it's easier to interact with language. So as you have seen in the first part of this talk, finding failures in vision model is reasonably hard. So on ImageNet, again, there's been many ways of testing models. The 2 most common ways is to basically either collect another data set, and here Hendrix and others have done tremendous work around, building ImageNet A or ImageNet O or ImageNet R. And these data sets are basically trying to test particularities of the model. So it can be about seeing how the model degrades when you have limited spurious cues, or it can be about specifically testing various distribution shifts. Collecting data is, of course, costly and requires people to label new images. And so people have also tried to create synthetic data. So the more common data sets used in ImageNet are ImageNet C, which is a synthetic set of common corruptions to test basically the performance of model against perturbations of images. There's also been stylized ImageNet, which tests basically how a texture shape Q conflict can change the decision of a classifier, and basically was used to demonstrate that some convolutional networks really emphasize texture over shape. And you can also have these data sets that are composites, where you take a background in a given set of images, a foreground object in another given set of images, and then you composite them in various ways to test basically how your model reacts to different foreground objects with different backgrounds. Again, this requires some human creativity. It's not always trivial to automate the process of basically extracting foreground objects, gluing it on different backgrounds, and making it look reasonably realistic. And so people have also tried to leverage more automated tools, which tend to scale better. So in language, you, of course, have the case of templates, where you create a set of templates for your sentence, and you try to replace different words or compose these different templates together in order to trigger a failure. We have, of course, the case of a norm-bounded perturbation, which can be used also as an interpretability tool. And finally, there's also a lot of work around leveraging generative model in order to create new adversarial images. But again, like the work I've seen so far were really about trying to explore the latent space in a way that would trigger failures in the different generative models. And again, like the process of knowing which latent to modify and how is quite complicated and difficult. And so that brings me to this last contribution, which was around discovering basically errors and failures in models using off-the-shelf image generation and captioning, which is our most recent publication. So obviously labeled data is very scarce, so scraping the web and rating images is actually expensive. Again, creating this synthetic data set requires creativity, so it's difficult to scale. And a lot of these tools are not really open-ended. And the case in point is for LP norms, which are really constrained to this mathematical set that we've predefined. And so here I'm going to describe basically a methodology where we leverage newer generative model that have been trained on web scale amount of data. They doesn't rely at all now on any expertly crafted heuristic to compose new images. It doesn't require that you recollect a new data set. You just have to collect your original data set once. And it allows to surface failures that are interpretable because we're going to caption these failures using a captioning model. And that allows also these captions to be queryable in the sense that somebody could go about, change a different caption and see what happens. And finally, we also demonstrate that you can scale this approach to generate new adversarial data sets if you wish. So this is a sneak. The most funny one might be the mushroom, which when it's turned upside down, the standard ResNet 50 would classify this as a candle. But we can generate basically almost any number of years. The setup I'm gonna skip because I'm running slowly out of time, but it's really the same as before. We have a classifier F for which we would like to find failures. And we're particularly interested in finding captions that would lead to inputs that we generate that have higher failure rate than a baseline caption. This might be better explained by this diagram here. So in the first panel, we're basically going to try and generate images from a baseline prompt. Here, in particular, we're interested in failures of flies. So on the fly class, so we're going to ask our generative model to generate a realistic photograph of a fly. This generates a number of images that we can classify, and we can also measure now the failure rate on top of these images for that baseline caption. We take all the failures, we can recaption them using a captioning model. In this case, we end up with a caption that looks like this. So the initial part of the caption is fixed because we know exactly which class we're trying to generate, but it will add details such as it is on a yellow flower and the background is green. That allows us to then generate much more images of that particular kind using the generative model again. We can measure the failure rate. And if the failure rate for that new detailed caption is bigger than the failure that we obtain with the baseline caption, then we can basically claim that we're onto something. And we found basically a set of a caption or a set of captions that tend to lead to higher failure rates. And finally, and this is perhaps the most exciting thing about this, is that you can take the caption and you can start editing it, either automatically. So in our case here, we just look at different subparts of the caption, or manually if you're interested about exploring the failures more precisely. So in particular, the flower is yellow. It might not be the main reason why the fly is misclassified as a bee. And in fact, if you ask for just a realistic photograph of a fly that is on a flower, you get the exact same failure rate as if the flower is yellow or not. And so we started by doing so I'm going to show two examples of failures. We picked two random clauses here, fly and crayfish. And we're going to look at two specific target classes. So how often the classifier misclassifies a fly for a bee, and how often the classifier misclassifies a crayfish for a chain link fence. And basically, by running this pipeline, you can discover these new captions. So one is, of course, the fly on the flower, but the other one is the crayfish in the net. And you can see that basically you can significantly increase the number of failures for that particular target class by just adding a different context to the core object of the image. You might wonder, so here we've used now ImageGen as a way to generate these images, but you might wonder how this fares with other generative models. So we've also tried the exact same caption that we've discovered with ImageGen on both DALL-E 2 and Stable Diffusion. And we can see that we can also trigger more failures for these particular captions. And finally, you might be wondering, well, what about real images? And then again, you can go to Google's image search, try to issue a query for these different captions, and you will also observe that the failure rate increases for these particular captions. Here are examples of a few more open-ended failures that we can find. Some are well-known, such as vehicles in the snow tend to be classified as snowplow. But others are maybe more exciting, like the sea lion jumping out of the water tends to hint that there might be a killer whale in the region, or the jellyfish that is, orange and bright and might be a torch. So finally, we can also generate a lot of these images at scale. We generate about 10,000 images for targeting a particular ResNet and a particular vision transformer. So you can see that you can measure the failure rates now either against the same model, which would of course reach 100% failure rate, but you can also look at what happens when you transfer these failures to other models. So here, a second ResNet trained in the exact same way would have basically a transfer rate of 78%. And as you go to vision transformer, that transfer rate will drop to around 54%. Images that we discover with the vision transformer would tend to be a better model, tend to transfer also better. And finally, you can also transfer to different models on ImageNet alone of different architecture. And you can see that most of the time you transfer quite well the errors that you found on a given data set. And the main reason probably is because the failures are basically grounded into language and they basically mean something relevant rather than just adversarial perturbations. There's a number of limitations, obviously. The generative model might not cover the space of all possible images. It might be really rare to generate, let's say, a Persian cat in the snow, which would often be misclassified as a lynx. You can't, so searching for the space of real images and the space of images that you can find using the generative model is definitely an open problem. There's, of course, bias that creeps in because you've used images from the web, which are biased. Here's an example of a blue crayfish. Blue crayfish tend to be overrepresented in generated data because people get much more excited about blue crayfish and take a lot more picture of them than there really are blue crayfish around in the world. There's also captioning issues. So because we ground all our failures to language, some images might be really hard to caption. So this is an example of a crayfish that gets misclassified as a chain link fence. It's very obvious to us why that is the case. The claws make kind of a shape of a chain link, but it's really hard to describe in the language, exactly how to position the crayfish in the claws to make that happen. And finally, obviously, you have problems with the generative model, and the generative model may sometimes generate image from domains that are not the domain you care about, let's say cartoons or drawings. And here's again an example of an image where we try to have a salt shaker next to a lemon. We end up with a lemon and salt, but no salt shaker. And so the outlook is that if we want to be able to train models that are reliable, trustworthy, we need to be really thinking about every step of the way, how we can correct the process and force correctness throughout. So we want to make sure that the data that we collect is of good quality. We want to make sure that training and fine-tuning is following specifications, and maybe calibration is also following specifications, that our evaluating procedure is really testing corner cases, both on real and synthetic data. And finally, we can deploy, and upon deployment, we should be able to adapt our models very quickly. So that brings me to the end. I'll take any questions now, and of course, feel free to reach out to me by email if you don't have time to ask your question. I'll stop sharing.
Okay, thank you, Sven. I think it's now time for questions. We will prioritize participants from Zoom, and then we will consider also the one that we have on YouTube. Okay, so in the meanwhile that we wait for the others, just one curiosity. Sven, regarding the first paper about where you actually use a generative model for preparing and for creating something synthetic data that would be later used for improving robustness. Do you have any idea or geometrical interpretation of what is happening for such a result? So for improving the accuracy, so the robustness. So.
Yeah, it's my interpretation of the easiest way to interpret this and how I would explain it is by saying that assume you have a very bad generative model that only samples uniformly across the pixel values. Obviously, most of the time it will generate garbage, but sometimes with non-zero chance, it might actually generate an actual image. Your model has kind of infinite capacity. You can make that mental exercise that obviously there's non-zero sense it might generate a sample from the test set. So my model can memorize it and it will do fairly well on that example from the test set. And so now if you want to go into more, deep understanding, I guess you have to understand about patterns more than just actual full images. But if you have a non-zero chance of generating a pattern that may appear in a real image, then that holds in the same way. And so I think that's why that system of just generating lots of random or generated data is good and works. Yeah, obviously it has limitations because you want to increase the probability that you generate real samples or real patches of images. Yeah, I hope that explains.
Yeah. Other questions from the audience? Okay.
Maybe I have a question. Regarding when you use generative data for training models and improving performances, how does it scale with the model size, for example, or with dataset size? I mean, I can imagine you need a lot more images for getting a little bit of improvement.
Yeah. So the number of images that you will need will highly depend on the quality of your generative model. I'd say for a diffusion model in CIFAR-10, we're getting really, really good images, which means that you can already see the benefits of those generated samples, even by just doubling the data set size. So another 50,000 examples. But obviously, the more you add, the better. And we've gone all the way to 100 million examples, generated samples. And you can definitely, as you add more samples, you get diminishing returns, and that can be explained in many ways. One is maybe we still lack diversity in those generative models, so we can't generate everything, and at some point it starts repeating itself, or there's an inherent distribution shift, an inherent difference between the generated samples and the true data, and the model might start learning particularities of the generative model rather than the actual real data. So,
thanks.
Okay, we have a question from the audience. Please go on, Battista.
No, yes. So first of all, thanks for the very inspiring talk. I think it's a set of impressive work and very useful for us. One curiosity that I have is that at the beginning you showed this idea of combining data with some external knowledge to build something more robust. But then from the talk, it seems to me that it's mostly, I don't want to say brute force in a sense, but the idea is to kind of use larger and larger models with more and more sophisticated augmentation techniques on data. And so my question is, even if we assume that we have a way of finding all these problematic failures, like imagine that we have these generative models that can find all the corner cases, or even in some mathematical terms, we can model some of them. Do you think that the solution will be still to try to learn all these data sets from these data sets, like using larger and larger models, or can we somehow hope to inject, some kind of knowledge in a more mathematical form, and maybe also try to learn smaller models. I mean, I don't know if the question is clear, but like what they do for instance, with ordinary differential equations, where you have a model of the system and you can embed it in the learning process. So what do you think about this?
Definitely. I mean, one of the things I didn't mention, but was in the slide because I was running out of time, but is the fact that it has to be human driven in some ways. Data can get you a certain way, but won't get you all the way. And I think the perfect example is the mugs, right? So like in that case, you would say, well, it's obvious we need to flip images, and we've been doing it for a long time. There's just, horizontal flip of the image, and that helps tremendously the network generalize. And that probably allows the model to be smaller and reach same performance. You can also try to embed in the architecture, obviously, the specification. So you can reduce the number of parameters, and like, let's say from the start, you want to be symmetric. You can embed that in the architecture and get a long way that way, reduce your model size and even do better, and training for less time. Things become more problematic for things that humans can't foresee. So I feel that there is a usefulness for tools that will, find corner cases, not necessarily all of them, but like enough of them to make you confident that, either you've addressed most of the corner cases that you care about in your deployment, or you found a corner case that you really feel is really important to address, and then you can go back to either incorporating that corner case with like an actual human-made specification that you discover, like that you write yourself, or you try to model it with a generative model and try to either augment your data or change the architecture as a way to address that particular issue.
Thank you.
Okay, we have one more questions from the audience. So the first one is from Nasir in Zoom. He's going to ask, to perturb the classifier, do we need to know the type of the network, the weights and the biases of the infrared classifier? Or we can generate random perturbation without the need to know what is inside the box, black box?
I mean, you can always assume you don't know anything and then go about randomly. That would be fairly inefficient. So the more information you have about the network you're targeting, the better you're going to do. And so, yes, like doing black box attacks or discovering failures through a white box scenario is going to be way more efficient than assuming you know nothing. But obviously, like in the case of the final part of the talk, I've assumed zero knowledge about the classifier. So even in that case, you can actually, if you have enough compute, basically you can start generating enough samples that you might discover something interesting. And that's particularly the case if you're not interested in finding all failures, but you're just interested in finding one. Yeah, obviously now adding, white box access to that classifier during the data generation process, for example, through classifier guidance, would be an extremely efficient way of creating things more quickly.
Okay, then we have a question from the YouTube channel. So from Christian, he's asking, thank you for the talk. Was it considered or could there be an improvement by combining stable diffusion image and only two generated images together with the original data set? I don't know.
Sorry, can you repeat? I just lost connection to.
Yeah, that's fine, thanks. Okay, there is a question from YouTube, from Christian actually. He say, okay, of course, thank you for your talk. And then he's asking, was it considered or could there be an improvement by combining stable diffusion image and only two generated images together with the original data set?
That's, I don't like the correct, the true answer is probably, I don't know. So I get his question. So obviously, if you think all of these models model different part of the data distribution, then combining them would make a lot of sense. So you would basically cover more real data, and you might be able to find corner cases using one model that another model doesn't find. My strong guess is that probably it ends up, these models are mostly trained on probably similar data. So it might be that they are very close in terms of the distribution of images that they generate. And as such, you may not gain as much from combining them. So yeah, I expect you can get the same results with DALL-E 2, definitely. Maybe Stable Diffusion for generating realistic images. I've had a bit more trouble, but yeah, you can definitely try with Stable Diffusion.
Okay. More questions from the audience?
So I have a.
Okay, we have Maura.
I have a question. Maybe it's just a silly question, but what happens if when you capture the images, then you refeed the thing many times? So you do the loop of creating an image, captioning, creating the image from the caption, etc. Does it drift away at some point, or I mean, is something you explored?
As to the whole pipeline. So one is we of course want to limit the caption size, and we want to keep the caption simple. So we basically limit it to 2 sentences or 3 sentences. They could be hallucinations, or it could be that you get a description that is about something that is not even in the image, and then you start generating that have nothing to do with the original failure. However, if you still find more failures, then the caption is still representative of this. And 2, if you don't, then you just haven't correctly captured the original failure, but it's fine because we're not interested in finding all failures again. I guess the biggest risk is when you end up basically having a correct caption of some form, or a caption that the generative model generates something completely different than what the caption really says, but the caption keeps saying the same thing in some sense. So there's the 2 models work in unison to agree on the same error in some ways. So in that case, you might surface failures that are not real failures and that don't correspond to the true label, which is probably the biggest risk. But hopefully you have some human in the loop at the end that observes everything.
Okay. I have just one more curiosity, Sven, if you have enough time. Yeah, you were discussing before about the fact that, for example, models such as DALL-E 2, Stable Diffusion generate images which belongs to where the distribution is quite, concentrated somehow. I'm curious to understand whether you think that, for example, we can use such models, such generative models, for, I don't know, solving the bias problem that we need, for our data. So we don't have enough data, for example, of a blue lobster. So we ask to this model to generate new data that will be used for training. So do you think they are going to solve the bias problem, or they will actually open a new kind of bias?
Yes and no, I guess. You might be able to fix some biases. The problem is you might shove the error further, in some sense that maybe the generative data that you generate also has bias. It's just a different one than the one that you were originally trying to learn or to correct. And so you might learn very particular biases of the generative model now. And when you actually, try again, you can run again the same method, assuming the captioning and the generative model kind of, at least the combination of those 2 will generate you images that might be unbiased for that particular caption. You might be able to find the errors again and so on and repeat the process, but I still feel it's quite a leap to say, yes, we can find failures, and yes, we can correct them. at that point, I'm not quite sure whether it's feasible to just generate more generated data to fix problems. What I would suggest to the practitioner is more discover the failure with a generative model, but then go to the real world, collect more data about that specific failure.
Okay, thanks. We don't have any more questions, so I think it's all for today. No, we have also Fabio, sorry.
Yeah, hi everyone, can you hear me?
Yes.
Okay, thank you a lot. And I wanted only to ask regarding the second work, if basically you leveraged GAN generative models because you wanted a kind of mapping between the Euclidean distance or LP distance in the latent space and the semantic distance, a kind of semantic distance in the image space. So what do you think about this, I mean, relation or link?
Yeah, I mean, yeah, I think as you point out, I think like the core idea is to say that in latent space, like the latents are more representative probably of the transformation you care about, and maybe the distance in latent space is more interesting for the particular transformation that you care about. In our case, we didn't even care about the distance in latent space because of the way the mixing property of StyleGAN works. You can just mix anything. So basically we were allowing, if you want, the radius of perturbation that we were allowing in the latent space was fairly large. It just has to englobe any possible latent that you might, any possible irrelevant latent that you might observe.
So thank you.
Yeah.
Okay, let me check if there are questions. So, on the YouTube channel.
So I think let's close the live streaming, and then if people from the Zoom chat have more questions, maybe if Sven has another 5 minutes, then we can keep going. So I want to thank again Sven. Thank you a lot for coming to our seminar. It was a pleasure to have you here.
Thank you.
And thank you all from the audience for participating. So we'll see you next time in the next episode of our seminars.
Thank you.
All right.
Okay.
Sorry for my connection.